Okay, so in this video, I'm going to be going through page 7 of the notes packet. I'm going to start with example 1 up here because I think it's the most intuitive introduction that we have. And that says, John runs a hot dog stand inside of a baseball stadium. The amount of hot dogs that he sells, H, is a function of the number of people who attend the game. The number of people who attend the game, P, is a function of the cost of a ticket to the baseball game, C. The functions below represent the situation. So we have the number of hot dogs as a function of people is equal to 0.15p. And the number of people as a function of the cost of going to the game is 8,000 minus 400c. So what do the functions h of p and p of c represent in the context of the problem? Well, h of p, that's the number of people, that's the number of hot dogs based on people in the stadium, right? So the number of hot dogs sold as a function of the number of people in the stadium. And P of C is equal to, that represents the number of people in the stadium based on the cost of the tickets. All right, so how many hot dogs will John sell if tickets to the game cost $5? So we have to figure out, if we want to figure out how many hot dogs John needs to sell, or how many hot dogs John will sell, we need to know the number of people who go to the game. We know, in order to figure out the number of people who go to the game, we need to know the cost of the tickets to the game, which we know to be $5. So we can figure out how many people are going to go to the game by plugging in $5 into P of C. So P of 5 is equal to 8,000 minus 400 times 5. That's going to be 8,000 minus 2,000, which is going to be 6,000. So we know if tickets are $5, then 6,000 people will show up to the game. So how many hot dogs will he sell? Well, now we can take that, right? So now we know 600 people are going to come to the game. But let's plug that into our function that will tell us how many hot dogs are sold as a function of the number of people at the game. So h of 6,000 is equal to 0.15 times 6,000. And if we do 0.15 times 6,000, we get 900. So that means 900 hot dogs are sold. All right, but what if we wanted to create a single function that told us how many hot dogs could be sold based on any ticket price for the baseball game? So we know we can start with h of p, that's 0.15p. But remember, this p, right, the number of people who come to the game, is itself a function of the cost of the game. So P of C is 8,000 minus 400C. So like we just saw in the previous problem, if we know a C value, we plug it into P of C, and whatever we get for the number of people at the game, we plug that into H of P, right? Our formula that says the number of hot dogs based on the number of people. So if we want to combine this, well, we know P is going to be the result of when we plug C into this function. So we can rewrite H of C by taking 0.15 when, instead of writing P, right, ordinarily we would write P there. Instead, we're going to write our function of C. So instead of multiplying 0.5 by P, we're going to multiply 0.5 by the function P, which itself takes C as an input. So 8,000 minus 400C, that means H of C is equal to 1,200 minus, I think that's right. Yep, it would be 1,200 minus 60C. And this tells us for any cost C to go to the game, how many hot dogs will be sold. And we can verify that this works. If we plug in 5 here into our combined function, we can see that 1200 minus 60 times 5 does come out to be 900. All right, so now we want to use this function to determine what ticket price would allow John to sell 1080 hot dogs. Well, so now we have the output of the function h of c, right? We know he's going to sell 1,080 hot dogs, and we need to set that equal to 1200 minus 60c, because that's our function that tells us for any cost to the game, for any ticket price, how many hot dogs are sold. So then if we solve this, we can subtract 1200 from both sides. That becomes negative 120 is equal to negative 60c. We can see that c would be $2. If tickets to the game are $2, then John will sell 1,080 hot dogs. And so this is a specific example of what we're going to be doing with a much more generalized thing with functions. So if you'll notice, we took one function, right? The function that told us the number of hot dogs sold. We took one function, the function that told us the number of people who will show up to the game as a function of the cost of the tickets. And we plugged that inside a different function, which told us based on how many people come to the game, how many hot dogs will be sold. So we're embedding one function inside another function. And we call that composition of functions. So you'll see that written like f of g of x. I prefer this notation because it's more intuitive. You take g of x and you put it inside f of x, right? I think that makes a lot of sense. But you'll also see this f of g of x. I remember that by thinking of the little circle there as the word of f of g of x. And then that makes me think of it like this. So if we look at some examples here, I'm going to color code these functions. So let's let h of x be yellow. Let's let g of x be orange. And let's let k of x be pink. So if we have h of g of x, then that means we want to take our function h of x, but instead of x, right, we would normally write this h of x, but instead of plugging in a specific value, we're going to be plugging in the function g. So h of x is equal to 1 over x, which means h of g of x is 1 over g of x, which is 3x squared plus 2x. So h of g of x would be 1 over 3x squared plus 2x. All right, and now we have, down here we have g of k of x. So similar thing. Right, we have g of x is equal to 3x squared plus 2x, and k of x is equal to x minus 1. That means that we're going to write g of x, so g of k of x. We're going to write g of x, but everywhere where we see x, instead of writing x, we're going to write the function k of x. So the function k of x is x minus 1. So that's going to become 3 times x minus 1 squared plus 2 times x minus 1. And so now we need to expand this a little bit and we can simplify by turning this into 3 times x squared minus 2x plus 1 plus 2 times x minus 1. Right, I just evaluated the square here, meaning that's equal to 3x squared minus 6x plus 3 plus 2x minus 2. And that means if we combine like terms, we get 3x squared minus 4x plus 1. And so this would be g of k of x. All right, and then we have one final one down here where we're starting with k of x, which is x minus 1. And then we have, inside of that, we're putting h of x, where h of x is 1 over x. So that means k of h of x is equal to, so here is k of x, here is h of x. Where we see the x in k of x, we're going to replace it with the function h of x. It's going to be 1 over x minus 1, right? Where 1 over x is h of x, and we've embedded it inside the function k of x, which is x minus 1. So a little bit of trickiness there, but once you get the hang of it, it's pretty straightforward. And we can also do this for specific values of a function in the domain. So for example, we have f of g of 2. We can also write that f of g of 2. And that means find the value of g of 2 and then plug the result into f of x. So g of 2 is going to be equal to 4 times 2 squared over 2 minus 1. Maybe plug 2 into the function over here. That's going to become 16 over 1. So g of 2 is equal to 16, which means f of g of 2 is the same as saying f of 16. Because 16 is g of 2. And then if we plug in 16 into f of x, we're going to get 1/2 times 16 minus 14. That's going to become 8 minus 14 gives us -6. So f of g of 2 comes out to be -6.